Do. Hope everyone's sufficiently motion sick now. If anyone has questions, the floor is open, so just feel free to chime in just on your mic if you want to, or in the chat and just ask a question. I'll try and answer it. Fire away, anybody.
So I'm trying to find the A-level problems within the chapter. Are those like within the conceptual checkpoint and skill builder?
End of chapter. You'll find most of those at the end of the chapter.
Yeah, it looks to start with 8.41 when you go to practice problems.
These A-level practice problems, they could be embedded. Typically, the lower numbers are embedded within the practice problems throughout the chapter. And they could be anywhere in there. And then once you get to the higher numbers, you're typically going to find those at the end of the chapter.
So with 8.11, it's asking about if an alkane is calcinated in the solvent as an alcohol rather than water. Reaction similar to acid catalyzed hydration, but in the second step, the alcohol functions as a nucleophile instead of water. And then it's got, what would that be? Looks like 2-methyl ethene.
I don't care about the name. What's the question?
Oh, it's just working through the mechanism of it.
Let's take a look at B. Question number B, 8.11b. Asks us to try and figure out what the heck happens that would lead to this alkene reacting with sulfuric acid. Okay, and apparently it is going to make this six-membered ring product like this. And the question is that's being asked is this analogous at all, or how so, to something simple like taking an alkene and adding water in the presence of H2SO4 instead. And if we were to do that, we would expect to add water across that double bond in a Markovnikov addition type process. So something like this. Is what we know about addition of water to sulfuric acid in any way, sort, of sort helpful in trying to figure out how, in God's name, this reaction took place. And certainly, whenever you see a molecule that has two different, here's an alkene functionality and an alcohol functionality, yeah, there runs the possibility that those things might react with one another. And man, what could we know about alcohol addition, water addition, hydration to an alkene that might be germane here? Let's see. It looks to me like there's one thing I'd like to just do before we get started, which might be numbering some carbon atoms. And so I'm going to start from this oxygen, or just atoms in general. 1, 2, 3, 4, 5, 6, 7, 8. So just kind of asking the simple question of where the hell are those atoms, if we're going to try and convince ourselves that that product is actually made when we add acid to that reaction, and it is. Makes it a little scary for the idea that you have water in your stomach and you have alkenes in your stomach when you consume something, and then your stomach is definitely acidic. So I wonder if reactions like this are taking place. Spoiler alert, they are. We could number the product. 7 and 8 could be interchangeable here, but I just want to make the case that, yeah, that thing does in fact make that product. How could we mechanistically rationalize what's happening with what we know with what could potentially happen here? Well, let's just kind of do this. If this, is it applicable here type argument. And yeah, let's see. Well, I have this starting alkene, and when I react HSO4H with that, so that's just a really poorly written version of just the proton sticking out of sulfuric acid. Nucleophile, electrophile, find my pen in here, always going to behave as a nucleophile, always going to behave as an electrophile. Where's that green? I guess it's this one right here. Electrophile and acid in this case. And so addition right here. It looks like we're going to follow Markovnikov addition. Hey, pretty straightforward. I've got another alkene over here. OH. I'll draw this a little bit better, hopefully. Aesthetically, that's a lot better. The behavior of this is not going to change. The behavior of this is not going to change. It looks to me like we have just Markovnikov addition of a proton, acid catalyzed, to an alkene. Looks like these two things are pretty similar to one another. Well, I wonder what happens next in this reaction over here. Well, the next step in this reaction would be taking this newly formed carbocation and reacting that in the presence of our nucleophile, which is water. And so, yoink, nucleophile. If this isn't obvious to anyone watching right now, make it obvious. It's a plus charge. What does the plus charge want? Electrons. And if a plus charge wants electrons, that makes this in a thing that loves electrons, an electrophile, and nucleophile here. And so the lone pair of electrons on that oxygen are a decent enough nucleophile to find that carbon center, and we could potentially, and I'm going to do this for us here, I'm going to write a squiggle line, OH, to just denote that there is the possibility of two chiral products. But the general idea that I really want to stick with here is that we get that water to add. Well, let's just not lose our minds. I guess that's the whole point. If I'm doing my job as a Sherpa for you all, if I can get you to not lose your mind when you see something like this, then I think I'm doing a good job. I got a water nucleophile that added here. I don't have anything left in my solution at all to react, but I do have something that could be considered a nucleophile right here. Yeah. When using a nucleophile like an oxygen that's tethered through all of, hold on, when it's tethered to the other electrophile, you just get a cyclical compound instead. But I think what I've shown you here, it seems pretty rational that at the very end, though, we just need to remove this proton right here. Same thing here. We just got to remove this acidic proton. We have a nice conjugate base that we could use to abstract that proton. And here we would be calling this a Bronsted-Lowry acid. And we'd be calling this other species right over here our Bronsted-Lowry base. But we could remove that product, and in doing so, that's an equilibrium reaction, we would end up generating the product that is suggested in the problem. And so, Dallas, I haven't answered your exact question because I want to leave that question up to you to figure out. But I have given you an example here of just what happens when we just substitute one of the protons on water with the R group instead. And so instead of using a water, we're using an alcohol. And it seems to me like from this proof, the chemistry is pretty much the same. It's pretty sound. And so, yeah, just using an alcohol there, I think you'd probably be able to rationalize 8.11a from there, methanol. Other questions anybody can ask. Feel free, please.
Could you also get a product with that where the OH acts as the nucleophile and takes the hydrogen from the sulfuric acid? And
Yeah.
there would be some result that I haven't worked through.
Yeah. Yeah, and Ian, I don't know if you saw the debacle that was the lecture earlier this morning. There was a little period in there where I went down that road actually in the example, and it turned out to be the wrong thing. For everybody that's listening and anybody that's going to watch in the future here, Ian just asked a really solid question, which is, could the alcohol actually react with the sulfuric acid instead? And the answer is absolutely. Yes, absolutely it could. And so how do you know which one it's going to react with? Well, in this question, we're really more worried about what's happening with the alkene instead. And so what I mean by that is you have a product that's drawn, and so you have to get to that product. And so you don't have to worry about a side reaction because you already have the product generated here. But just to go through the actual question, which is fantastic, could I potentially react the alcohol instead with that sulfuric acid? And yeah, I've got a Bronsted-Lowry acid here. I've got that's not the right color. This one right here could behave as a Bronsted-Lowry base. And in that example, I would see the use of this lone pair here to abstract that proton in a Bronsted-Lowry equilibrium type reaction. And the product that we would generate instead here would be an OH2 plus. And so now we have an incredibly good leaving group. And so perhaps we see loss of leaving group as well. In formation of, we're kind of going down the substitution reaction review here with water forming as well. And I'm going to tell you, Ian, that yes, this could happen. But this species right here, it's just going to want to react with the next best nucleophile, which is water, which is a better nucleophile than this alkene. And so what ends up happening is we just get this whole thing going back in reverse. And that's kind of the thing that happens with leaving groups is once you make a leaving group leaves, it always has that option of returning and getting right back to where you're starting. And so what I would suggest to you with this fantastic question is this chemistry I've highlighted right here, this chemistry is taking place all of the time during this reaction. It is taking place as a side reaction to this thing happening here. But because it leads nowhere, it just makes this and figures out, hey, that's not energetically favorable, and just goes back until this species can find a different path, which is this one right here.
Gotcha.
Yeah, it's a great question. It really is.
Well, yeah, that was my follow-up was, like, as a rule of thumb, is one or the other, the alkene versus the OH group, going to be a better nucleophile in that case?
Yep. I think like an advanced OChem class or a grad level class, I would ask you guys to figure out which nucleophile is out competing one another. But unlike what I did in lecture, and this is one of those instances where I missed my class because I would have seen all the panic looks on your faces and aborted that line of thought. But when we're talking about alkenes in this point in time, you've got a 99.9% chance if you start reacting the alkene as a nucleophile and finding the plus charge in solution, that's going to be right for this exam. I'm not going to try and throw a curveball of saying, hey, look, this OH is here as well. Which one is going to react first? That's not something I want you to worry about. In this instance, just like in this question, 8.11b, react that alkene first, and then use the alcohol later. We've had a few more people log on. Please just, if you've got a question, feel free to ask. Really anything, you can just name out any question, really, and I'll try and take a look at it with you. We've got another 40 minutes together if you guys want to utilize it. Just to kind of make this just straightforward with everybody watching this and here together, if I end up eating this entire bag of family-sized chips together, no one can talk about this. It didn't happen. Perhaps one thing that I could do that might be helpful for everyone here while we try and find a few more questions from the audience would be to just take a look at the differences that we could find in just the... If I keep telling you that all we're doing here is changing up the variant of alkene that we have present, let's just play a little game here of saying, let's outline the different types of alkenes that we know about, or more importantly, pi bonds, and just ask ourselves, how would each of these pi bonds react, and just kind of to maybe drive home the idea that these are all similar. So let's just kind of make a table. Alkene is the functional group name. So let's just say that we have a let me just say type of pi bond. And so we're going to be looking at an alkene here. And so the example of that would be R, something like this, generically. And so perhaps a good example of this would be this alkene. So I'll write generic, an example. And then saying, how does this sucker react with HBr? What type of products would be formed from the addition of this HBr? And then we're just going to go through every other variant that we kind of have right now. This HBr addition, we would add a hydrogen to the thing that has the most hydrogens on it. So an H here. and then we would have a Br, and I'm going to do the squiggle line, and those here we'll know that that denotes that both enantiomers could be present. You could draw this with the wedge and write plus enantiomer. That squiggle just means that it could be either R or S. So we have the potential here for an enantiomeric type product being formed. Okay, so that's not too bad. Type of pi bond, alkene. And then let's just say that this alkene is conjugated. And I haven't used this word at all in lecture, but I could right here just say isolated all by itself. But here we have a conjugated type alkene. And so the example here might be taking this 5-membered ring and have this really beautifully conjugated system here and just asking the same question. What happens when we add HBr to this conjugated alkene? And remembering that from today's lecture, we could get the 1,2 addition, which is the kinetic product, and that would be 2 possible products, an R and an S, if applicable. And then we could also generate, when these types of alkenes react, squiggly line like that. Oh, that doesn't look so good late at night, but that's the idea. You follow. That's the 1,4 addition, which is the thermodynamic product, because you need that extra energy to make that secondary, that hydride shift, or the resonance shift product as a result. What else have we talked about? Oh, pi bonds, yeah. How could I forget? Alkynes. And so looking then at how would this same reactant react with a terminal alkyne, and just giving this a nice example of a terminal alkyne like this, adding HBr, and I'm just going to write one equivalent here to acknowledge, if we were to control the stoichiometry here, that the hydrogen would add here, bromine would add here, opposite of one another, and then another equivalency here. And don't forget, there's one implicit hydrogen. There's one that's been hiding the entire time. But those really are really kind of the whole summary. I just came up with this on the fly. I'm kind of pleased. It kind of summarizes how, with one reactant changing the different types of pi bonds that we're seeing, what types of reactivity you would see. This doesn't do much for us for oxidation or reduction reactions, but those aren't mechanistic based. You can memorize those, but for all the rest of the addition reactions, this kind of summarizes it. Other questions or thoughts or concerns, things I can address?
I guess this is a concern more than a question.
Yeah.
Would you like us to show mechanisms for every other reaction in the test?
Oh. Divine.
Yes.
You must think I'm a very sadistic human being. The answer to your question is there will be instances where mechanisms might be warranted or might be asked about specifically. But there are other instances where you just merely have to show the reagents that are required to make a reaction take place, or the products or the product that would be formed. And in those instances, let me just give you an example. Let's just say that what you see right here in the bottom right corner is very similar to the examination, but you right here in this picture you would see a question mark with a number 1, and you would have to generate the product from starting from this part right here, adding hx, and you would have to come up with this being the product, let's say. Now, you could use mechanistic thought here because it is an addition reaction to help you get to this product, but I would not ask you at all to draw the mechanism for that one reaction, because you're going to see on this exam that most likely 35 points are just going to be dedicated to, do you know the reagents that made this transformation, or do you know the product or reactant that was used in combination with the reagents or the product or reactant. So what I'm saying is knowing mechanisms when you can to generalize reactions may be helpful in just these really straightforward questions of know the reagent or know the product. Now, taking it one step further, here's an example of a question that I was thinking about for the examination, but we just covered for this review session, but I'm actually still thinking about holding on to something very similar here. Here's an example over here where we have been working exclusively with the use of water. And I might say on the examination, hey, guess what? You can use an alcohol instead. And not only can that alcohol, can it be an alcohol, it could be an alcohol that's still attached to this molecule. And at that point, I would say, why don't you complete the mechanism with the arrows that you would need? And I would draw everything in black and ask you to produce all of the things in orange. And so when I ask you to apply something that you've done to a slightly new instance, I wouldn't ask you to come up with this mechanism on your own, but certainly I think you could. I would ask questions about this mechanism that would ask you to say, hey, draw the arrows that represent where the electrons go. And I know that was a really long answer, but hopefully the takeaway was use mechanisms if they help you with the memorization of reagents. And then you may be asked about mechanisms specifically, but when you are, it wouldn't be to ask you to generate a whole mechanism for this problem up here. That's just not something I want to do to you. But perhaps filling in the missing parts, yeah, that would be fair.
Right. Thank you.
Yeah, absolutely, kid. Maybe that'll be the goal for these sessions. Like I can get like a can of Pringles, and if I'm not eating because I have to answer questions, that's the idea. So you don't want me to consume, but then if the Pringles are gone, then the sessions are over. Perhaps that's the way to go. Anybody else? Other questions I can answer? It can be about anything too. If I were to pontificate, since this is on camera, about the examination, I have a very simple examination philosophy. It's this like 85-10-5 idea, which is I think that all that's up to 100, right? 85% of the examination should be things you've seen before, and if you can, and by that I mean fill in the reagents here. And so it's stuff that we have seen before that I'm asking you to regurgitate in a slightly altered but still pretty much straightforward format. And if you can get all those questions right, then great. You're sitting at that B level. And then the next 10% is going to be questions that ask you to take the knowledge that you have and then kind of extrapolate it to not too far of a stretch from where you're comfortable. And I couldn't think of a better example of asking you to make a slight stretch, but not necessarily making you come up or generate this idea on your own. But I'm saying, 10% of the exam is going to be asking you to take something you've seen before and apply it to a slightly new situation, in which I'm asking you to use the skills, like drawing the arrows here, to fill in some missing information. And then just 5% of the examination, I'm really gunning for maybe just stuff you haven't seen before, or applications that you might not have seen before, or maybe even just a short essay question. And when you look at that 5%, you're looking at 2.5 points on the examination because it's out of 50. 2.5 points out of 50 really is all it is. And I find that separates the A pluses from the Bs. And in those areas, I'm really looking for deep knowledge and understanding of what's going on. But what I'm really trying to relay to you is I'm only looking for extreme deep understanding and separation of student understanding with less than really around 5% of the examination. I am not looking to crucify you, to murder you, to try and drive home how smart I am, because I'm not. I'm really just trying to say 85% of this exam, are you running where you need to be? And so don't think I'm giving you an examination where 85% of it is just going to crush you. That accomplishes nothing. That accomplishes nothing in a learning environment. And so that's kind of my philosophy here. So hopefully the people that stumble on this video can see that, and hopefully it's reassuring. I don't know how much of that is going to feel like on the examination when you're taking that, but no, deep down in my heart, that's what I'm really shooting for. I don't want you thinking that you haven't seen this stuff before. That just isn't the point. That's not the point of education. What do you think the decorum is about, like, drinking red wine whilst essentially teaching a class? I mean, if we were in Garwood, I couldn't do this, but I don't know. I think it may be a perfect sacrifice for invasion of privacy. We'll have class at home.
The flask and no one knows.
Oh, goodness. The real secret is I mixed whiskey with this red wine instead. That'd be horrible. Other questions, people? Things that I can. Oh, let's go through another example if you keep looking for questions here. I have been telling you this. We've been using a generic example of an alkene, and I'm just going to stretch it out right here and just do something a little wild and crazy by just saying, let's take a look at this residue attached to this weird arrangement of atoms, and then ask ourselves, let's add water to this in the presence of sulfuric acid, and then kind of ask ourselves, what is the product that we would expect to see from this reaction? And then after we've asked that question, we can kind of go back and say, is there something that I haven't been teaching you, haven't really spent much time on in class and have only alluded to? And what I've been saying is in class is that when we look at addition reactions to alkenes, that typically if we were to build a scaffold, which you can almost always do by just retaining the sigma portion of this, the sigma backbone of the molecule. All I'm really saying, I'm really turning into a professor here, and that was just one sip of red wine. I got to stop. We would expect the chemistry to take place here, is all I'm saying. If the region of the molecule where the alkene existed was there, then I would expect most of the time the region of the chemical change to occur on really the same carbons. But then every once in a while in your notes, you've noticed I've put a star right here. It said sometimes every once in a while you might want to look out. I don't know what's happening with this camera, but we'll fix it for tomorrow's lecture. Every once in a while, it might be chemical change that occurs here too. Can we justify what's going on? And so let's kind of extrapolate with this addition of water molecule that we're doing in the presence of H2SO4 as well, and just see if when we can come up with the instances that this might be an instance where chemical change actually occurs on the adjacent carbon to where our alkene was. And I think this is going to be pretty... I don't think I'm going to teach you anything surprising here. Let's mechanistically... and so I can't remember who asked the question about the mechanism here, but this might be an example. I'll try and give this example to you right here in a manner that you might see on an examination. So I'm going to suggest that the regiochemistry doesn't exist here. So let's draw out the actual product of this reaction, and then I'll phrase this in a manner that that we would probably see on an examination. Plus an enantiomer. And so the question that you may see on an examination is, if I were to be eloquent and on top of my game when I write this, we would anticipate the following product, which would be, I'll just write, again, the movie thing is great. We would expect this product using our theory, but the product that was actually obtained from the reaction was this product. Complete the mechanism that shows how this reactant reacted with these species to make the unanticipated product, and it's an enantiomer, rather than the anticipated product. And maybe I would write then, question A would be, draw the mechanism that accounts for the formation of the anticipated product.
So with something
Keep
like this,
going.
right? Because we would see a hydride shift.
Who's doing this? You're ruining the whole show for everybody.
I'm sorry. I was just curious because wouldn't we also, in addition, see the expected product as well as the hydride shift?
Dallas, you are right on point. Yes, you would see the actual the anticipated. You would absolutely see the anticipated product. Let me toss this to you. Can you think of an example then, or conditions that we learned about today that would more likely generate this product over your anticipated product? So let's say that there are reaction conditions that would generate more anticipated product, but there are also conditions that you could control in the laboratory that would generate more exclusively this product. What is that other thing that's missing from this arrow?
Temperature.
Yep, you got it. Higher temperatures, more likely to produce this here. Less lower temperatures, more likely to produce this here. And so, your great questions. Keep them coming, man. Draw the mechanism that accounts for the formation of the anticipated product. That's really what we did with something like this mechanism right here. And so, since that isn't necessarily a departure from what we've seen in class, yeah, I wouldn't give you very much. Maybe I just say, draw the mechanism that accounts for the formation of the anticipated product. Like that. And you'd have to generate the whole thing by yourself. But then I'd say B, complete the mechanism that accounts for the formation of blah, 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 the actual product formed in this hypothetical world. And for that, then, what I would give you would be something like this. I'm just going to kind of stop talking for a second so I don't screw any of this up, and then we can come back in and fill it in. But if you were to see this on an examination, you would likely see something like this. Oh, I got to do this without actually completing it. You can do this. You got your PhD. OH2 line angles diagrams, just to note, seem to depreciate as we go further into the night, but you all are intelligent enough to understand what we're trying to do here. And so you would see this on the examination. Complete the mechanism that accounts for the product formation. And for that, then I'd be really asking you some questions about saying, how did we actually get to this thing that we didn't anticipate, you know? And the idea would be that you identify that this double bond will behave as a nucleophile, this will behave as a Bronson-Lowry acid, and so we get this type of nucleophilic attack or a Bronson-Lowry acid base type reaction, formation of this carbocation. But noticing that, and I'll come back through and supplement these notes even with some more stuff. But just going quickly, a hydride shift to move this hydrogen and its electrons over, and now we have a secondary, tertiary carbocation for which is suitable for attack by water. And then we just need to remove that one proton. I should put a plus charge right here to get our final 1, 2, 3 1,3 addition to that alkene. And perhaps that's even one of those, a half a point of that 5% of the exam would just be, what would you call this addition? If we know that 1,4 and 1,2 conjugate addition work, what would you just arbitrarily call this? And just 1,3 addition to generate this product. And so why is this this example, why does this take place? You're really looking at a secondary carbocation v a tertiary carbocation, and so carbocation stability prevails. I'm just gonna, there might be a question, but I'm just gonna keep going. Where else could this show up then on the examination? Potential energy, reaction progress. Perhaps then I'll have a reaction coordinate diagram that looks like this, and I'm just going to keep drawing this so you would say what you might perhaps see on the examination, and then I'll come back and supplement this with some potential questions that you might see. I'm moving really fast now. Now the hand hurts. OH2. So maybe draw all of this stuff and ask you to draw the structure here, perhaps identify all transition states. Could be a question. Identify all intermediates. So just, perhaps match these structures to positions on the mechanism. Again, I'm hopefully illustrating what that 85% of the examination is going to look like. Certainly never sat down and asked you to specifically do that, but now I'm asking you to tie together some really straightforward themes. Here's the potential energy diagram, reaction coordinate diagram. Can I match that to each of the steps in a mechanism? Can I show where that energy is? Or even asking the great question that Dallas asked, or that I asked Dallas, because I asked it, but what would be the thing that we could potentially even use to differentiate formation of these products, and that would be temperature. Perhaps that gives you just kind of an idea of how these questions can start to show up and tying together what we've been doing over the course of this, short week together, really. Other questions or thoughts? People kind of keep trickling in, so I'm glad people are attending. I hope this is this is helpful.
Is that outcome also something you can control with your solvent choice as you have a drink of wine?
Yeah, good question, Eon. You know, as I said, practicing synthetic organic chemist, there's large combs and there's small tooth combs that you can use to try and impact things like regiochemistry or stereochemistry. And temperature is one of the big things you can use to impact regiochemistry. And solvent choice is something that is a fine tooth comb that you can sometimes utilize to your advantage after you've solubilized your compounds to try and differentiate between products as well. It's all messy, man. It's never easy. Very seldom can you create a reaction that only produces one product over another. In fact, there's a man out of UC, no, get this right, Cal, UC Berkeley, K. Barry Sharpless, and he actually developed a way to synthesize enantiomers, R versus S, to like a 97:3 ratio by utilizing, believe it or not, this is how brilliant. You know, and if you look in scientific history, the solutions to some of the biggest problems in the world are really so simplistically elegant and beautiful that it's no wonder that it worked. Carrie Berry Sharpless took tartaric acid, which is found all over the place, and it comes in two different enantiomers, and he, just by mixing tartaric acid with the right solvent, was able to generate one R in 97%, and then if he changed and used the other enantiomer of tartaric acid, he's able to control the S formation in a manner that that is really utilized almost for any type of reaction, and that won him the Nobel Prize and bukus of cash because he patented that and uses it all the time. And so obviously there's a big need to selectively make one thing over the other, because you're looking at the difference between tossing away 43% of your product or being able to convert 43 more percent. And if you're trying to get a cake, it's nice if the tiniest little piece, if you have to sacrifice any of it, it's just the tiniest little sliver. But yeah, it's messy stuff, Ian. It's really messy chemistry, and you've seen it in lab with me. I mean, I felt so bad teaching you OChem before they took us away from each other. But like, here's the solution. Put it in your round bottom flask and just heat it with this thing. And to be honest with you, that's what PhD chemists do. It's still messy.
Cool, thanks.
Yeah, man. Just to, since we've only got a few more minutes, but I'll utilize the time as effectively as I can. Let's just talk about like how you could, on an examination, you might see something that looks like like this, and it says HCl addition, and it says like question 9 is that, and all I'm really asking you is to predict the product that was formed from this reaction. And on the answer sheet, if you were to write this, you would get plus 1 point. If you were to write this, which is the incorrect regioisomer, guess what? You still got the idea. You know that HCl is being added. You just kind of you flipped and flopped when you didn't need to. Plus 1/2 point. plus 1.5 points. And so the idea there is the more you are rewarded for getting things right. You are rewarded for getting the regiochemistry correct. You are rewarded for getting the right addition of stuff correct. And then you are rewarded for getting the stereochemistry correct and acknowledging it's an enantiomer. And so maybe this question would be worth 1 point, and you get a bonus half point for getting the enantiomer right. Maybe I make it out of 1.5 points. Typically, my exams are over 50 points anyways by a few. So the idea here is that you can't just get a 0 because you didn't get this. And I just think in education, me personally, other professors require a different level of precision, and that's on them. But for me and what works for me in my class, look, this is all sorts of right. There's a lot of right. There's what I was able to do, and then there's what I hope you at least get. But I still want to reward understanding. I still want to reward effort, and I want to do it on a scale that everybody can potentially win. And so just know that things are rewarded based on level of correctness. I'm adding HCl. If I identify the addition of HCl, but I miss regiochemistry, I'm still going to get half credit. If I am understanding that I'm adding HCl and I add it with the right regiochemistry, Markovnikov addition, I'm going to get full credit for that. And if I actually remember that sucker's got an enantiomer and the potential for, in this one example, the right stereoisomer and it's an enantiomer, I'm going to get an extra half bonus point for getting that complete understanding. And so just know that if you don't get this, you still got shots at other things. Let's do this for tonight. This is a good example of what these sessions can be. Let's call it for tonight. We will have another one of these tomorrow. We will have another one after that. So hopefully our classmates will see this video and can kind of see what can be obtained from this. For those that were here, you can kind of see that how quickly one simple question, I'm able to turn that into a lot of different talking points. And so knowing that, please join me tomorrow and just bring one question each, and you'll be surprised how quickly we can fill the hour. We'll give everybody their chance to enjoy the evening, and we will reconvene tomorrow morning. Enjoy your evening, and we'll call it for the night.